Welcome to the LNG Maritime Odyssey, a concise expert tour from liquefaction to regasification. In this presentation, we'll explore the technologies, vessels, and operations that move natural gas across oceans as a cryogenic liquid, and the safety, commercial, and environmental frameworks that make global LNG trade possible. Think of a single molecule's journey as five linked stages: upstream purification, liquefaction, maritime transport, regasification, and downstream delivery. Each stage transforms the gas physically and commercially while introducing specific technologies and risks, and together they form the integrated value chain that enables reliable energy movement across the globe. Before gas can be chilled, it must be cleaned. This slide highlights common impurities like water, acid gases, mercury, and heavy hydrocarbons, and shows the treatment train: acid gas removal, dehydration, and mercury and heavy hydrocarbon capture that brings CO2 down under 55 ppm and prepares the stream for safe liquefaction. Liquefaction is the great compression where natural gas is cooled to around minus 162 degrees Celsius and shrinks to roughly 1/600th of its original volume. This step makes long distance shipping practicable but is highly energy intensive. So, plant design, energy source, and efficiency are central commercial drivers of the process. The engine of liquefaction uses refrigeration cycles, typically either cascade systems with multiple pure refrigerants or mixed refrigerant loops that match cooling curves more continuously. Hybrid approaches like propane pre-cooling combined with a mixed refrigerant final stage balance efficiency, footprint, and operational flexibility for modern LNG plants and floating units. An LNG carrier is essentially a floating cryogenic plant, integrating containment, propulsion, and gas handling to move cargo at minus 162 degrees Celsius. The vessel includes cargo tanks, boil-off gas systems, cargo manifolds, dual fuel engines, and the navigational bridge, all coordinated to preserve cargo integrity and ensure safe, long-range transport. Two dominant containment philosophies exist: Moss spherical tanks that are self-supporting and robust against sloshing, and membrane prismatic systems that maximize cargo volume through thin primary membranes supported by insulation and the ship's hull. Each offers trade-offs in space efficiency, structural behavior, maintenance, and suitability for different vessel sizes. Boil-off gas is inevitable as small heat ingress vaporizes some LNG, and it must be managed carefully. Common strategies are routing BOG to fuel the ship's engines, re-liquefying it on board to preserve cargo, or controlled combustion in strict circumstances. Effective BOG management protects safety, economic value, and regulatory compliance. Cross-ocean voyages expose LNG carriers to harsh weather and ice risks like slamming, sloshing, and hull impact. Mitigation combines weather routing, speed and heading adjustments, sloshing management through tank operational limits, ice class hull design, specialized crew training, and the use of icebreaker escorts or satellite and charting tools for safe navigation. The final mile at port demands precision and coordination between ship, pilots, tugs, and terminal operators. Pilotage, berth, and draft constraints, mooring plans, tug maneuvers, and port state inspections must be synchronized to protect safety and avoid delays, because successful arrival depends on clear communication and exact execution. Regasification terminals perform unloading, short-term storage, pumping, vaporization, and send out to the pipeline grid. Their core job is to return LNG to gas safely and reliably while balancing inventory against downstream demand, which requires tight coordination between ship schedules, terminal capacity, and send-out rates to maintain supply stability. Vaporization technologies each have distinct roles. Open rack vaporizers use seawater or fresh water for efficient heat transfer. Submerged combustion vaporizes LNG in a hot water bath but emits combustion products, and ambient air vaporizers rely on ambient conditions for low emissions. Choice depends on site resources, environmental limits, and operational reliability. Floating storage and regasification units combine onboard LNG storage with a regasification plant to provide rapid market access and flexibility. FSRUs offer speed to market, lower upfront costs, and redeployability, but require robust mooring, regulatory alignment, and matching onboard capacity to market demand and local conditions. Behind every technical decision sits a framework of international codes and industry standards that enforce safety and environmental performance. Bodies like the IMO, SOLAS, MARPOL, the IGC code, and industry groups such as SIGTTO codify practices for ship design, operation, and pollution prevention, embedding a culture of compliance across the LNG chain. The Odyssey continues with innovations that reduce BOG hybrid containment concepts, broader FSRU deployment, and digitalization for predictive maintenance and optimized operations. These trends point toward greater efficiency, enhanced safety, and a more sustainable maritime LNG ecosystem as technology and regulation evolve together.